Hello everyone. So today we're going to discuss about how we can arrive at this Hamilton's equation of motion. Okay, written here. So this is Hamilton's equation of motion. Okay, so the goal of today's uh, lecture is to derive this set of first order differential equation, or this relation, so-called Hamilton's equation of motion. Okay, so let us recall what we learned in the previous part of this lecture. So we have defined Hamiltonian function, h denoted by h, which is a function of, or which is mathematically written as pk qk dot minus l. Okay, so and this, what we have seen is that this h Hamiltonian function now is a function of qk, generalized coordinate, generalized momentum pk, and time. Okay, so this is what we have seen. Now also we know that the Lagrangian L is a function of, you see, qk dot and t. Okay, so what we are going to do is we're going to move from, say, a Lagrangian formulation of the mechanics to Hamiltonian formulation. Okay, that means a function, okay, the dynamics of a system which is described in terms of this function Lagrangian qk dot and t. Two, we're going to make a new set of equation, or equation of motion, which will make use of this function h. Okay, no, sorry, which is defined in terms of generalized coordinates, momenta, and time. Okay, so how do we do this is via a Legendre transformation. Okay, and Legendre transformation is normally used for various other purposes in thermodynamics as well. So what we have to make a note of this is that, in the Lagrangian function, the argument is qk dot and t, and in this Hamiltonian we have pk. So we try to get rid of this time derivative of the generalized coordinate qk, and now use this generalized momenta pk in the new function h. Okay, so so before we move ahead with the derivation, or to arrive at the Hamilton's equation, as we said at the beginning, let us make a very a small remark, okay, about this formulation. So Hamiltonian formulation, this is what we call, okay, this is an alternative to Lagrangian formulation. Okay, this is one thing. And what is interesting is this way of uh, describing the dynamics in terms of Hamiltonian function is, particularly useful in, say, particularly useful in dealing with problems of modern physics. Okay, in dealing with problems in modern physics. Okay, so we will use Hamiltonian in other topics, say in quantum mechanics, in other areas of modern physics, but for today's lecture our focus is on the equation of motion that involves the Hamiltonian function. Okay, so let us move ahead and do this. So as we said, so the goal of today's lecture is to describe the motion of the system in terms of equation involving Hamiltonian function h. Okay, so and we also said that it is a nothing but a coordinate transformation problem. But anyway, let's just start. So as we have written already, the Hamiltonian function, okay, uh, so we know that the Hamiltonian function h, okay, is the dot minus Lagrangian L, which is, let's just write for completeness sake, qk dot and d. Okay, so this is one thing. And now also write, so h is a function of qk, pk and t. Okay, let's just put this as equation number 1 and equation number 2. Okay, now let's take a differential of these, dh. Okay, dh is, we can write as, you see, del h by del qk dqk plus del h by del pk dpk plus del h by del t into dt. Okay, so this is the first step. So let's put this as some equation number, say 2a. Okay, and this equation 1 also we can write del h equal to dot dpk plus pk, then our d qk dot minus dl. Okay, so let's just put this 1a. Okay, so now what we have to do is we just have to write for Lagrangian also the dl. Okay, so what is dl? L is a function of qk dot and t This implies your dl is can be written as, you see, L by del qk dqk dot plus del L by del qk dot dk dot, this is okay, and plus del L by del t dt. Okay, so this is another thing. So we can use this, put the value of dl in this. Okay, so we just have to uh, put the value of dl here using what we just described here. Okay, so let us just do that, and equation looks like this. Okay, so the dh is summation del h by del qk dqk so what we have to do is we have to, okay, let me just write this as okay, we have to use this in 2a. Okay, then what it looks is this. Okay, del h is summation qk dot dpk plus summation pk del qk dot. So now instead of dl, we just have to put the value we just got in the last. So del L by del qk d qk minus pk del qk dot minus del L over del t into dt. You see, so in these two terms already cancel, this one and this one. So what is left here is the following. Okay, so say dpk, this is the first term, and this negative del L by del qk dqk minus del L by del t into dt. Okay, so here we have to know what this is actually. So we have to get this from the Lagrange equation of motion. We know that d by dt of dl by del qk dot is equal to your del L by del qk. Okay, and this here within the bracket is nothing but this is our momentum pk. So this implies del L by del qk is nothing but our dpk by dt, which is pk dot. So we just use that and rewrite these things. Okay, so dh looks like this: k qk dot dpk minus k, then pk dot dqk minus del L over del T into dt. Okay, let's just put this equation number 3. Okay, so this equation number 3 has to be compared with this uh, equation number 2a. Okay, let me just write here equation 2a here. What was it? 2a is summation del h over del qk d qk plus del h over del pk d pk plus del h over del t into dt. Okay, so if we compare, okay, so comparison will give us the following. Okay, you compare this equation of this same coefficient here, this and this and this and this. Okay, so what we get here, you see, from this first, qk dot is equal to del h over del bk, and from the second one we have negative pk dot is equal to del h over del qk. So this is the normally what we write as Hamilton's equation of motion, and this also has the third term. This comparison between the last term will give us negative del L over del T is equal to del H over del T. Okay, so these are the sets of equation here that we normally refer to as the Hamilton's equation of motion. Okay, so so let me just write 1 second here. Okay, okay, so what we have said is qk dot is equal to del h by del pk, and negative pk dot is equal to del h over del qk. Okay, so this is what we have said. Okay, this is Hamilton's equation or Hamilton's canonical equation of motion. Okay, so this is what we have just derived, and another thing to notice here is, as we also discussed in the last lecture, this is a set of 2n first order differential equation. Okay, whereas the Lagrangian or Lagrange equation of motion is a is or consists of, okay, and second order differential equation. Okay, so this is what we have to know, the difference between the Lagrangian equation of motion and the Hamilton's equation of motion. Okay, so up to here we have just derived the equation of motion in terms of, you know, Hamilton's function, and it turns out to be a first order differential equation. Okay, and this will make the calculation easier. As always, first order differential equation is easier than the second order differential equation. In the next lecture we will continue with the applications, okay, applications of this Hamilton's equation of motion, meaning how do we use Hamilton's equation of motion in solving dynamical problems, okay, in dynamical problems. Okay, so let's work out some interesting problems in the next lecture together, and for today let us stop here, and I hope you uh, enjoyed the lecture and understood, hopefully understood. Okay, then see you in the next lecture.